Okay, before going into technical stuff, I want to mention our imaging research team at the Quality and Safety Assessment Research Unit, Athens, Georgia of USDA-ARS. Brian Bocco is our research leader for the unit. And then we have quality and safety related projects within the unit. And we have Dr. Hong Zhuang doing sensor research, and then also new quality project leader Byung-Hui Kong doing DNA related study, and we have a postdoc. And in the safety side, we have Dr. Boson Park sitting over there as a project leader, and then we have PhD student helping on the research. Uh, First, my primary research area is development of optical imaging technology for poultry meat quality and safety assessment. Machine vision using color cameras presents a practical and cost-effective solution in many cases, especially for numerous poultry industry applications, such as real-time detection of abnormal coloration and shapes. However, color-based imaging systems exhibit limitations in tasks requiring analysis of meat composition uh, or characteristics that we can talk about later. They struggle to detect certain safety contaminants or subtle quality variations not discernible through color signatures. Hyperspectral imaging is modality. Oh, sorry. Um, it's basically it's based on the use of spectral signatures in image domain. So in today's talk, I'm going to talk about several different projects that we conducted for the past 20 or so years, including woody breast detection and white stripe peak detection. From port quality side, I'm going to also mention about the hairline crack detection for table eggs, and I'm going to also talk about the detection of foodborne pathogens as presumptive screening technique for colonies on agar plates, detection of fecal contamination chicken carcasses, and also wholesomeness detection in poultry carcasses, and also talk about the detection of foreign materials in specialty crops and broiler breast fillets. First, I'm going to talk about the foodborne pathogen detection using hyperspectral imaging for presumptive positive pathogen detection on agar plates. Hyperspectral imaging technology was developed to screen colonies on agar plates to detect and classify the types of Salmonella, Campylobacter, and Shiga toxin producing E. coli, so-called STEC, by extracting unique signature from spatial and spectral perspective. And so using this type of technology, we can take a look at the shape and spectral signatures that hopefully can unique to each type of pathogens grown on agar media. And then we can use the machine learning technique and then detect and then count and then identify types of pathogens. Hope that this technology can be help to the regulatory agency like FSIS, where they process a lot of samples daily basis, so that we can hopefully can reduce the cost and time for their the screening process. So for Salmonella detection, this particular slide shows the XLT agar media grown with Salmonella enteritidis and then Typhimurium. And so after applying hyperspectral imaging, we can detect individual colonies, and then as you can see here, hyperspectral can basically label each pixel and also colony as different colors so that we can easily identify, and then we can um, produce the numeric numbers. Um, and also, this slide shows the detection of Aztec on rainbow agar, modified rainbow agar. And so in this particular study, we used the one hyperspectral imaging system in our lab and then developed our own model and then transferred that model, basically software, to different system in University of Kentucky. And then without any further change, they were able to almost reproduce what we created in our lab. I mean, in our case, we had 100% detection accuracy, whereas they missed only one case. It was about 99.6%. So it's called technical perspective is called calibration transfer. And then in most recent years, we used AI technique basically based on 3D convolutional neural network to look at the way of classifying the variety of different types of Aztec cell bars. I mean, in this particular study, we used 15 different Aztec cell bars, and then the accuracy was about 90% when you use AI technique. So that was very exciting technique because the microorganisms, when they were grown, they are very similar in many cases, and then there are very large variation sample to sample and then week to weeks. And for this particular study, we conducted this study over the 3-year time to ensure that that variation can be captured through this machine learning model. But still, I think the model still is not perfect because although we collected the data over the 3 years, but due to the nature of the data collection, which is very time-consuming and laborious, still the data set is not good enough, I believe, to deploy for the practical use. This is the somewhat limitation of hyperspectral imaging when dealing with this type of samples. And so this is slightly different technique, but still we use the microscopic spectral imaging technology to look into cells under microscope. And so for this particular research, we use the basically label samples through the so-called fluorescent institute hybridization probes for multiplexing. So we were able to demonstrate that we can rapidly and accurately separate two different microorganisms through this technology. And so now I'm going to switch gear a little bit to talk about the high-speed hyperspectral multispectral imaging technology for food safety assessment. For this particular research, we look into a way to detect foreign materials and also fecal contamination on chicken carcasses. So we developed this technology to detect wholesomeness, which is systemic disease on chicken carcasses, and also the surface of fecal matters on in chicken carcasses. So we started with the spectroscopic study to develop models, and then we further studied using pure spectrum-based so-called hyperspectral imaging technology. And when we developed this technology, and there were very limited hardware resources available, and so we had to develop the multispectral imaging where we deployed a 3-band-based algorithm. And so using one hardware system and the one software application, we were able to demonstrate the 2 different applications can be put into that system. So one system was to detect disease detection, and the other system was for fecal matter detection. I'm sorry. So basically what it does is to detect the disease as a whole. I mean, when the chicken goes by, at 140 bursts per minute in portrait processing plane in the US. And the other application is to detect the fecal matters on the chicken carcasses. And so the basic technology is based on line scanning. So just to keep in mind, then when you talk about the hyperspectral imaging technology, we are not talking about area cameras. Detectors are area detectors, but the scanning mechanism is typically is line scanning. So that the actual scanning should be done line by line. And so there are several factors and parameters affecting the design of the system when we are talking about the high-speed real-time hyperspectral imaging technology for portrait processing. And so in this particular case, we were able to demonstrate the hyperspectral imaging camera system is viable for portrait processing plant. And so the key of that is the recent development is camera technology. Because maybe 20 years ago, there were no such cameras dealing with this type of the requirement. But nowadays, there are several cameras on the market are available, providing very high frame rate, such as 500 frames per second or even 600, 700 frames per second. So that's what we are talking about. And so for this particular technology for detecting fecal and disease detection, we developed 2 or 3 bands for that particular case, and then we were able to implement it at about 500 frames per second to meet the production line of portrait processing. And then we also demonstrated the technology using the hyperspectral camera, producing the about over 100 bands and 150 bands, and then the scanning rate was 300 to 600 frames per second. And then still, the hyperspectral imaging camera is very expensive, depending on what you're talking to, who are talking to as manufacturer. And some people charge you about over $100,000 depending on what's in the package, and then as low as about $30,000 as a bare-bones system. And then our research was done to use the color camera to emulate hyperspectral imaging technology. And so I'm going to briefly talk about that, what it is. And so we, as I said, we developed a multispectral hyperspectral imaging model to detect the wholesomeness, fecal matters, and also the pathogens on agar media. And then the idea was, what if we use the color camera? Is it possible to mimic what spectral imaging can do? Yes, to some degree. So this is the results after applying color camera through a simulation and basically machine learning technique. And then we were able to demonstrate that we can reconstruct. So on the left is the raw data from the hyperspectral camera. On the right is the reconstructed hyperspectral data using color camera. So as you can see, they follow very similarly, okay? And then, so by the way, so the key technology to detect foreign material, the fecal matters on chicken carcass is looking at this slope of normal skin versus this slope of fecal matters. So that's how we came up with for multispectral technology. So to implement that multispectral technology, we don't need full spectral data. As long as we can get those slopes, then we are okay. So this study demonstrated that would be feasible. That means we can use a color camera to mimic what we have for multispectral imaging technology. And so these are the reconstructed images using the technology versus original spectral data. They are very, very close spectrally. but they are not perfectly matched with some errors. And so we also conducted the performance of our algorithm and then compared the results. And as you can see here, they are very, very similar, but it's slightly less accurate, maybe 2 or 3% accurate. Um, and so now I'm going to talk about the real-time hyperspectral imaging technology for foreign material detection. So the first part of this project was done in collaboration with Edward Photonics, hyperspectral camera manufacturer, and also CleanLine, which was a system integrator using robot. And so basically the concept of foreign material detection is by now is familiar with audience. And so what we did was we started with the multispectral technology first, using 10 bands, and then we implemented that technology into the whole system with the robot as a picker. And then we also tested full hyperspectral camera system, implement the algorithm, and using also the robot. And because I don't think this, oh, now it works. So the first batch of samples don't have any foreign materials. By the way, these are the craisins that ride the cranberries. So the robot doesn't move. Doesn't mean that it's looking, and the camera is off screen, looking at it, and nothing is there, and so no action is made. And so now there's so yeah, you can see easily that's foreign material as an example, as a demo, yeah, and over there, yeah. So that's what we did, and so in recent years, we use a similar technology to detect foreign materials in protein. And we started with the sensor fusion by looking at the technology from 400 to 2,500 nanometers in full visible and NIR spectral range. And then we determined that the sensor fusion would be probably the most accurate technology because it has everything in visible and the NIR spectral range, but it's very costly, and then it's very cumbersome to implement such a system. And then we narrowed down the spectral range to 1,000 to 1,700 nanometers, and we developed the AI technique based on the so-called generative AI. It's very rudimentary generative AI. The basic idea of foreign material detection for our take is to use semi-supervised learning, because most of studies using hyperspectral camera systems are based on the supervised learning, where the samples or target are trained. So meaning that when you talk about the foreign materials, then there are a variety of different types of foreign materials for training. So that means you have to collect the data from foreign materials. But in our approach, we didn't have to collect any data whatsoever for foreign materials, because in semi-supervised learning, what you need is to know what the good products are. That's all. And then anything abnormal can be detected. So this is very widely used in military applications, anomaly detection, or in financial sectors to detect the fraud of the credit card usage. Okay, so we use a very similar technology so that we only need the very abundant samples from chicken meat. And then we train the model just based on that as needed, and we can keep adding the data. Then all you need is just use the model from the good model, the normal samples. And And as I said, our model is based the very rudimentary generative AI, but technically it's a generative adversarial network, it's so-called GAN. I'm not going into the details about the technology. And so basically it has a generator and discriminator competing each other, and then at the end of a training using only the normal chicken meat, the model is trained to know what the normal chicken meat is. And then once the volumeter comes into the camera system, then it has, say, okay, this is abnormal, and then it produces the probability of the normal or abnormal. So that's how it works. And then we basically trained the model using two channels because we realized that the chicken meat is not homogeneous at all, and it consisting with a lot of muscle and also fatty materials. And then so that we divided into two models, and the one model is only looking at the muscle, the other model is only looking at fatty materials, and then the results are combined together. And this slide shows the spectral responses from the true original spectra and then synthesized, because just to keep in mind that this model basically generates spectral data automatically, synthetically. Okay, that's how this AI model works. Okay, and so as you can see here, so they are very closely following up to 2,500 nanometers, but our model cuts at right here because there are two different camera models available on the market when it comes to NIL, spectral imaging technology. One is based on InGaAs, which runs through from 1,000 to 1,700 nanometers, less expensive than the other one, covers from 1,000 to 2,500 and go beyond. And so we are more interested in less expensive hardware piece. So that's how we studied. And then in over the past 1 or 2 years, we have focused on how to deploy this technology when the AI model tends to be very complex. And so we tend to keep an eye on the development of NVDI. They have optimized so-called inference engine. So we utilize their the advancement to demonstrate this somewhat complex model can be deployed for hyperspectral imaging. And so just in summary, so our model, when it was properly trained, and it showed it's over 6 times better than using just the regular GPU. So we are still using the same hardware, but through this optimization, so we were able to use that. So as you can see here, when you talk about how many hyperspectral images can be processed per second, we can process up to about 70 hyperspectral data cubes per second through this modeling. So that's quite high speed. And then, how many minutes do we have? 5 minutes, okay. I'm going to talk about the quality assessment research. And so we use the hyperspectral imaging technology to assess various parameters related to poultry quality, including pH, tenderness, wall-holding capacity. And also we study to detect poultry meat defects such as PSE, DFD, white strapping, wood breast. And we also studied the way of fusing the different information to enhance the accuracy and detectability of those parameters, especially for tenderness and wall-holding capacity. And but most of these studies were academic, I would say. And I'm going to just highlight a few of the research activities that we conducted in the past. First one is to detect the hairline crack detection. So this is not hyperspectral imaging technology. It's just based on the machine vision technology using backlight. So basically, it used the vacuum so that any crack can be popped open within the vacuum chamber. So there's a camera looking down and then captures the moment of the crack opening. And then we implement a very simple image processing algorithm to detect. And then it shows how many cracks are in that chamber. So we have the listening system can accommodate up to 60 eggs at a time. And so, as you saw, it's very simple technology, but very effective technology. And also, we just the spin off this project to develop the software for demonstrating the way to collect the data electronically for AMS. So which study demonstrated how the data can be entered electronically and then processed. And we also developed a software system to process data using data warehouse to store and then process. And then another technology that we developed was to use hyperspectral imaging and also color imaging. We started with the hyperspectral imaging technology, and later we quickly realized that color imaging may be okay to detect white striping. So this shows the one example using color-based image processing technology. As you can see here, it's quite challenging to accurately delineate the white stripes, because it's still very challenging to even experts which white is really white striping. I mean, there's a variety of different degrees of white stripes. Okay. And now I'm going to talk about the woody breast detection. For this study, we studied the use of hyperspectral imaging, because we are the group using hyperspectral imaging, and then we saw the potential of using hyperspectral imaging, but we soon after using hyperspectral imaging technology, we realized that, okay, we have a better idea of using just the machine vision technology. That's I'm going to talk about it. And we also used so-called optical coherence tomography, which is subsurface surface imaging technology for microstructure analysis. We also use a 3D imaging technology to analyze the shape morphology of the woody breast syndrome. Yeah, as I mentioned, we used the hyperspectral imaging technology, and then we were able to see the efficacy and the feasibility of hyperspectral imaging technology. We did not publish this work at all, and then move on to different technology. And before going into that, I'm going to talk about the OCT technology. As I say, this is not for let's say, the rapid detection technology, but this is for more analytic technology to assess how the woody breast tissue will look like compared to normal tissue. So after going through the image processing, we were able to see the epimysium thickness was different between two groups. And so, yeah, due to the time limitation. So as I said, we use the machine vision technology. This technology is basically looking the woody breast bending from side. So this is patent technology. It characterizes the bending as it goes by over the end of conveyor belt system. And so this is final slide. So this is power hyperspectral imaging technology to display the difference between DFT sample and the normal samples with the pseudo colors. And finally, I'm going to briefly mention about what's going on in ARS research in Athens, Georgia. So we are currently working on the use of AI combined with hyperspeed imaging technology for foreign material detection, and we are also trying to enhance the accuracy for woody breast detection using the side view machine vision technology. We are also using multi-sensor fusion technology for assessment of multiple quality aspects of protein meat. And I think this is it. Thank you very much.